Today we will be presenting ABC-LMPC, Safe Sample-Based Learning MPC for Stochastic Nonlinear Systems with Adjustable Boundary Conditions. This work is in collaboration with researchers from UC Berkeley and Caltech. We will discuss the following question. How do we enable efficient policy learning across variable start and goal states in stochastic nonlinear systems without violating user-specified constraints when only sparse cost feedback is available? Over the course of this presentation, we will design a general theoretical framework to solve this problem and discuss its theoretical properties. We will then discuss its limitations and motivate a possible practical instantiation of the algorithm. We will then present a set of simulation experiments illustrating that the practical algorithm can still empirically maintain the theoretical properties we discuss. The framework we will discuss constructs and reasons about safe regions of the state space during policy optimization. This general idea has been a popular approach in recent work, with different formulations of safe sets that have been used in both model-based control and model-free RL. For example, safety can be implied by the ability to recover to an initial state, or safe state, or can be applied by the ability to reach a goal set. In this work, we will consider the latter implication, as the ability to successfully complete a task will imply the ability to be safe. This concept was proposed by Rosolia et al. And is called Learning Model Predictive Control, or LMPC. LMPC-based strategies have been used in practice to autonomously control real systems such as full-size cars and surgical robots performing knot tying. The LMPC framework maintains a safe set of states from which a prior policy was able to reach the goal set. The learning-based MPC controller can go outside the safe set as long as it can return back to the safe set should it need to. This allows it to iteratively improve. Under specific conditions, this strategy is provably safe, task completing, and iteratively improving. We proposed a reinforcement learning variant called SAVED, which uses system identification with stochastic function approximation to approximately provide these properties in stochastic nonlinear systems. Prior work shows these theoretical properties for deterministic nonlinear systems and stochastic linear systems for single start state and goal sets when optimizing worst-case costs. In this work, we will generalize these results to stochastic nonlinear systems and variable start and goal sets when optimizing expected costs. This results in a controller that can safely explore and improve to brand new start and goal configurations while maintaining the same theoretical properties in more general dynamical systems. The goal adaptation strategy we will use reuses data from prior goals when possible to define cost-to-go functions for new goal sets. This is similar to hindsight experience replay, where data is relabeled to match the goal that was actually attained and not the desired goal. This is also similar to prior work in robust motion planning, where reachable sets are combined in a graph or tree data structure that can be modified to adapt to new goals. However, unlike these methods, we will use a model-based planning approach to guarantee safety and task completion when transferring to new goals. In this work, we will discuss how to design an iteratively improving controller that is guaranteed to be constraint-satisfying, convergent, and improving during learning. We will first discuss how to do this for stochastic nonlinear systems in the case of a single start state and goal set. Then, after discussing the theoretical guarantees, we will generalize this to novel start states and goal sets while still maintaining the same guarantees. A theoretically motivated algorithm will be difficult to run in practice, so we will then present a practical instantiation of this algorithm and show that it can still maintain the proved theoretical properties empirically on simulation domains. Let calligraphic X denote the feasible state space. We use this to mean the set of states that satisfy pre-specified problem constraints, such as velocity constraints and obstacle avoidance. Similarly, denote the set of permissible controls by calligraphic U. In this work, we consider stochastic nonlinear systems, where the randomness is due to a noise input, and the dynamics are deterministic, conditioned on the noise input. The set of noise inputs is W, and we assume that noise inputs are drawn from a known distribution and that W is bounded. At execution time, we observe a noise realization drawn from this distribution, but we will design a controller that satisfies problem constraints robustly over W, while minimizing expected cost to go. We assume that the dynamics have a known parametric form, which takes in the current state, current control, noise input, and outputs the next state. We consider a very general class of dynamics models, allowing it to be nonlinear and stochastic, but time invariant and discrete time. Let us now define some basic notation. Let x superscript j subscript t define the state at time t of iteration j. We will use superscripts to denote iterations and subscripts to denote time steps within that iteration. We use this notation for controls, policies, and noise realizations. Let calligraphic G denote a goal set, which is a subset of the state space that we would like the system to converge to. In addition to this, we define a cost function that takes in the current state and control. We assume that the cost function is 0 inside the goal set, and lower bounded by some positive value everywhere outside the goal set. This value can be arbitrarily small and still provide the same theoretical properties, but the rate of convergence to the goal set may be slower in theory if it is smaller. We will require the goal set to be robust, control invariant. For a dynamical system F and policy class pi, a set is robust, control invariant if there exists a policy in pi that can robustly keep the system in the set for any state in the set. This also implies that if one is already in the set, it is possible to stay in the set forever. This is a desirable property, as it may not be possible to converge to sets that are not robust, control invariant. In this work, we will let our policy class pi be the set of Markov feedback policies. Therefore, we will require that our goal set is robust, control invariant. This intuitively is required to give us the ability to converge to the goal set, since to converge, we need to be able to stay there once we get there. Let J superscript pi of x denote the expected cost to go for policy pi from state x. We can recursively define this as the current cost plus the expected cost to go from the next state. We can also define this as the expected sum of costs over all future time steps for pi. Observe that since the cost in the goal set is 0, and the goal set is assumed to be robust, control invariant, the sum of costs over an infinite horizon can be written as a sum over a finite time horizon for successful trajectories. In practice, we will terminate episodes after a fixed horizon, but we will use the infinite cost to go estimator with discounting as in prior value learning literature. Now, let us define robust reachable sets. We will use calligraphic R superscript pi sub t of x naught to denote the set of states that the system can be at after t time steps when pi is executed from x naught. We let SS superscript j denote the union of robust reachable sets for pi superscript j over all time and the goal set. This intuitively is a set of states that can be visited by pi superscript j and the goal set. By construction, this set is robust, control invariant, as the system cannot leave this set when executing pi superscript j from x naught. If such a set is contained in the feasible state space, then we know that the controller is safe. Additionally, if the robust reachable sets eventually are contained in the goal set, then we know that the controller converges to the goal set. If we had a controller that satisfies these properties, then we can always revert to executing it as long as the safe set for it is robustly reachable from the current state, even if it is outside the safe set. This mechanism can enable the controller to safely improve, and is the fundamental idea that is used by LMPC controllers in different settings. We would like to solve the following infinite horizon optimal control problem. At iteration j, we wish to minimize the expected sum of costs from starting state x naught such that state space constraints are robustly satisfied. However, directly solving this is very difficult, as it requires searching over a large class of policies and optimizing it over infinite time. Additionally, it may be hard to guarantee that the policy optimization procedure maintains safety and iterative improvement. Instead, we will use an MPC-based strategy to iteratively and safely improve. The proposed controller improvement strategy is not necessarily optimal, but it will be guaranteed to be safe, converge in probability to the goal set, and iteratively improve at each iteration until convergence. MPC is a popular approximation to this problem, in which the controller optimizes trajectories over a fixed horizon, executes the first step in the plan, and then replans. As discussed earlier, the core mechanism of LMPC strategies is restricting the domain of the cost-to-go function to a set of safe states and constraining terminal states of the MPC planner to fall robustly in this safe set. We will generalize the guarantees of prior work for this class of algorithms to stochastic nonlinear systems with variable start and goal states. We'll show that safe states in this context will also refer to states from which a prior controller can complete the task. Intuitively, this is like maintaining a backup plan to a region where we already know we can perform the task, and therefore also be safe. If we go outside this safe set, the planner believes there is a better plan than simply executing an old policy, but it still maintains the option to revert to the old policy. In this work, we restrict the value function v of pi superscript j to the safe sets of all prior policies. That is, we let it be defined on states from which we have a policy that can maintain safety and task completion. We take a minimum over all prior policies' expected cost to go, as we can always choose which old policy we want to use. If the state doesn't fall in the safe set for a particular policy, then we let the cost to go be undefined for that policy. With each iteration, the value function v is defined on an increasingly larger domain as we add the safe sets for each new policy to its domain. Intuitively, we become confident in more regions of the state space over time. For now, we will assume we have an initial controller pi naught. We will assume that its expected cost to go is finite. In practice, we might be able to construct a controller using other optimal control strategies by behavior cloning a demonstrator or by hand tuning a PID controller.
Now let us discuss the specific MPC optimization problem we will solve instead of the infinite horizon problem discussed earlier. We will step through each of the components one by one. We let J super J be the planning cost for state x sub t super j with the planning horizon of h steps. The objective function is the expected cost to go of a sequence of Markov policies starting in x sub t super j, followed by the expectation of the minimum expected cost to go of a prior policy at the end of the horizon. Conceptually, this is like optimizing a sequence of policies over h steps, as long as we know that we can execute an old policy at the end of the planning horizon. Because we replan at each step, we may never actually execute an old policy, but we would always like to maintain the option to do so. We refer to the primary objective function as the planning cost. We will solve this problem such that constraints are satisfied for all noise realizations. Note that while we desire robust constraint satisfaction, we are optimizing the expected sum of costs and not the minimum sum of costs. The same results can be proved with a little less machinery for the minimum sum of costs, and this does not require knowing the distribution of noise disturbances. In practice, however, this may be a pessimistic strategy, so we focus on the expected sum of costs here. The first two constraints simply require that 1, the policy outputs a valid control, and 2, that the state sequences in the plan satisfy the system dynamics, which are assumed to be known. The third requires that the terminal state of the plan fall robustly in the safe set of the plan. And finally, we require that the possible state sequences robustly satisfy user-specified state space constraints. We'll now go over the main theoretical properties for establishing policy improvement. The first result is recursive feasibility, which essentially states that if the policy can find feasible solutions to the MPC problem discussed previously, then it will always be able to do so. This implies that user-specified constraints will always be satisfied, and will also lead to convergence in probability to the goal set. Note that since we assume an initial feasible and successful policy is provided, recursive feasibility implies feasibility for all subsequent iterations. Instead of going through the full proof, which can be found in the paper, we will instead discuss the main ingredients and intuition of the proof. In particular, the proof leverages the fact that we always have the option to execute an old policy. If we found a better policy, then we can execute it, but we will always maintain the option to revert to an old policy. Since the old policies are all robustly constraint satisfying, then the new policy is as well. The second result states that the system converges in probability to the goal set. Intuitively, this should hold because we know by assumption that the cost function is lower bounded by a positive value outside the goal set and is 0 in the goal set. From the previous lemma, we know that the expected sum of returns of the controller is bounded. If for any t, the probability that the system is outside the goal set were lower bounded by any positive value, then the expected cost to go would be unbounded, contradicting lemma 1. The third theoretical result states that the controller iteratively improves an expected sum of costs each iteration for a fixed start state. Intuitively, this should be true because we can always execute an old policy if we desire. We should only execute new behaviors if we know we will outperform prior policies, which we can know because we include the expected cost to go of prior policies in the value function. The proposed algorithm has desirable theoretical properties for fixed start states and goal sets. However, these limitations are not necessary. To roughly see why we should be able to change our start state, observe that we should be able to start anywhere outside the safe set as long as we can robustly plan back to it. We will propose an iterative procedure that expands the safe set by sampling safe start states outside of it. Additionally, we should be able to reuse prior data for new goal sets if the new goal set contains one of the reachable sets in the old safe set. Roughly speaking, if the new goal set is along the way to the old goal set, then we should be able to reuse a prefix of the old safe set. Now let's generalize this strategy to novel start states and goal sets. First, let's discuss the policy domain, or the set of states where we can robustly plan to the safe set of a prior policy. Note that this includes the safe set. However, This also can include states outside of the safe set. So even though a prior policy only visited a certain set of states, we can actually start off in regions outside the set as long as we can plan back into it. In particular, this should allow us to safely explore through the state space to become feasible at desired start states, without actually requiring demonstrations or an initial controller. Initially, the safe set could just be the goal set. It is easy to show that this maintains the properties of the safe set for some policy. We can now start the first iteration at any state that can robustly reach the goal set in each steps. How do we actually compute what these states are? To do so, we can actually solve an initial optimization problem that starts off in the goal set and optimizes an exploration cost to produce plans which go outside of the goal set, while requiring that the plan robustly returns back to the goal set in h' steps, where h' is greater than h. We can now select any state and the last h robust reachable sets of this plan as a start state, as we know we can robustly return to the goal set from it. So, after solving this optimization problem, we can run the LMPC strategy from this new start state. We can further expand the policy domain by again running the same exploration cost optimization strategy to find new start states. Now, suppose we want to reuse our data to adapt to a new goal set. How much data can we reuse to do so, and how do we do this? Recall that the safe set is a sequence of robust reachable sets for a policy. For intuition, imagine that these sets are disjoint and eventually contained in the goal set. If we specify a new goal set that contains one of the robust reachable sets, we can then reuse all of the robust reachable sets that lead to this goal, and then pretend that the remaining reachable sets are a subset of the new goal set, which is required to be robust, control invariant. This also requires slightly modifying the value function definitions, and further details regarding this procedure can be found in the paper. The theoretically motivated algorithm proposed in this paper has several extremely beneficial properties. However, it involves solving a formidable problem at each time step. We present a practical instantiation of this strategy that uses samples to approximate robust reachable sets and deep function approximation to estimate the cost to go of prior policies. We also plan over open loop control sequences instead of feedback policies and use the cross-entropy method to optimize the objective function. In this section, we will present simulation experiments in 3 stochastic nonlinear systems, evaluating whether the relaxed practical algorithm can safely optimize controllers and consistently complete the task during learning, seamlessly transfer to novel goal sets, and learn to perform tasks from novel starting configurations. For all experiments, a trajectory cost less than 50 implies convergence to the goal set from the current start state. We first present experiments evaluating whether ABC-LMPC can maintain feasibility and performance improvement when the start state and goal sets are fixed. We then present experiments where the controller 1 adapts to new start states with the goal set fixed, 2 adapts to new goal sets with the start state fixed, and 3 adapts to new start states and goal sets simultaneously. First, evaluate ABC-LMPC with a fixed start state and goal set on a noisy, constrained navigation task where the task is to guide a point mass to a goal set on the other side of an obstacle. At each iteration, we run ABC-LMPC and collect 5 trajectories with the current policy. We then use these trajectories to train a cost-to-go estimator for the value function and a state density model to approximate the safe set. The system is provided with an initial 100 demonstrations that are generated by guiding the system northeast until it'll pass the obstacle and then running unconstrained LQR. These demonstrations are suboptimal and have a mean cost of 44.76. In all experiments, we report results across 3 random seeds and present mean and standard error. In the single start, single goal set case, we observe that the sample-based LMPC strategy converges in 1 to 2 iterations to near optimal performance, shown in red. The algorithm never violates constraints and always reaches the goal set. A more greedy strategy might initially try going straight to the goal set and crash into the obstacle. We also present results on a 2-dimensional 7-link arm, where the robot must actuate 7 joints to guide its end effector to a target position while avoiding a red obstacle. ABC-LMPC is provided with 100 hand-tuned demonstrations that reach around the obstacle with a mean cost of 37.77. Each iteration again collects 5 trajectories with the current policy to train a new cost-to-go estimator and safe set density model. Again, ABC-LMPC converges to a near-optimal solution in around 5 iterations, never violates constraints during learning, and always successfully reaches the goal set during learning in all 3 runs. We then study how the policy domain expansion strategy can be used to iteratively expand the policy domain to contain new start states. For the point mass navigation task, these new target start states are denoted by S1 and S2 in these figures. In the tables on the left, we show the evolution of the start state over iterations and the mean trajectory cost when planning to G0. We find that for both desired start positions, S1 and S2, ABC-LMPC is able to iteratively shift the start position from S0 to both of the new start positions while consistently completing the task and never violating constraints. We observe similar results on the 7-link ARM domain and find that the policy domain expansion strategy safely enables the agent to learn to do the task from novel start states while consistently completing the task from each new start state. Evaluate ABC-LMPC when the goal set is switched after a couple iterations. We show the mean trajectory cost for reaching goal G0 in blue and for reaching goals G1 and G2 in red after switching to these goals as illustrated in the learning curves on the right. We observe that the controller seamlessly transferred to the new goal sets, which are illustrated in the plot on the left. We find that even when the goal set is switched, the learned controllers do not violate constraints and consistently reach the new goals. We observe similar results on the 7-link ARM domain and find that the controller immediately transfers to goal G1. We make the goal set larger in order to make sure that we're able to reuse sufficiently many samples from the original goal set. Finally, we evaluate ABC-LMPC on an inverted pendulum task where the controller must adapt to changing start states and goal sets. We initially set the goal to be the bottom vertical position and then use the start state expansion strategy to select start states further up vertically. When the agent can switch to the inverted vertical goal from a new start state, we switch to it and find that the algorithm is able to maintain an inverted position. Current and future work, we plan to investigate how to connect the ideas of ABC-LMPC to robust motion planning, such as robust RRT, by using robust motion planning to globally explore the state space and using LMPC to refine the solutions, which may be jerky or suboptimal. We will also study practical instantiations of this framework to visual domains, where we plan to investigate learned latent representations for safety and planning. Thank you for listening to our talk on ABC-LMPC. To summarize, we design a controller that improves over time while guaranteeing task completion and constraint satisfaction. We study this controller theoretically and prove these properties for stochastic nonlinear systems. We then discuss a practical implementation of this algorithm and evaluate it on 3 simulation domains to show that it empirically maintains the properties designed in the theoretical framework.